So for this second exam question, I actually decided to use a balloon as an analogy for mine. So to start us off, osmolarity is like the measured amount of helium within a balloon. The tighter the rubber of the balloon is, the higher the concentration of helium there is. You can see in the box that I labeled as 1 in the top left corner, there's a balloon and there's also a helium tank. So the helium that is being spewed out from the tank would be going into the balloon. Now, moving on to the second box, we're going to be discussing osmosis. So when talking about osmosis, water can be represented by the balloon being drawn to things using static. The friction a balloon causes against, pans or carpet or anything like that creates static, which is what moves the balloon toward other balloons. And like water, it always moves toward higher osmolarities or higher concentrations of balloon. Now, particles that can't cross on their own could be represented by a tennis ball, as you can see in the third box. Without an assistant protein, which is, just like a person squeezing, pushing the tennis ball in through that little hole of the balloon, the ball wouldn't be able to make its way into the balloon. It needs physical assistance in order to do it, which is the assistant protein channel. Moving on, particles that are likely to cross without assistance could be represented by oxygen. Now, for this one, let's move back to box number 1. As you can see, I have used 2 different colors to indicate different types of gases that are in the balloon. So I had the blue represent helium, which is the majority of what is filling the balloon. But that little pink sliver is just different gases such as oxygen or CO2 that may have seeped in when the nozzle or the balloon shifted, or when the balloon was being tied to keep the helium in. Now, for this next task, we are going to be using 2 balloons as a demo. The goal of this task is to get each balloon the same size, which is how I'm trying to represent having the same osmolarity inside and outside of the balloon, because each balloon is outside of the other balloon. You see what I'm saying? I hope you understand. Now, say 5% of the helium tank is what fills a balloon to its maximum capacity, or osmolarity. In order to get all of these balloons to osmotic equilibrium, we would need to get 5% of helium in each balloon, thus making the osmolarities inside and out the same. Now, as you can see in the 4th box, I have drawn a balloon that is normal, ideal at max capacity, which is on the left-hand side, the 5%er. Now, what we want to do is have the osmolarities within each balloon be the same. So if it had started off, as I demonstrated, at 3%, we would need to inflate it so that it would hit 5%, the normal and ideal max capacity. Now, once it hits that, we're at equilibrium and it's smooth sailing from there. All right. Now, moving on to tonicity. Tonicity can be represented by the max expansion of the balloon. It can be represented by the disfigurement or size of the balloon. If the tonicity is too high, the balloon will be more than likely to have lumps, which would be visible to the naked eye. And if you go down to the very bottom of my diagram, box 5, you can see that I have demonstrated 7% in there, which is too high. It would make the cell hypotonic. It would need to deflate by 2% to hit that maximum, nice, normal, and ideal capacity. And to continue with that, it would also be visibly obvious to the naked eye when a balloon is too small and doesn't have enough helium within it. That would make the cell or the balloon hypertonic, which is too low. So what we would need to do is take that 3% balloon and inflate it all the way until it hits 5%. And once it hits 5%, then as you can see to the right of the 3% balloon, it would become perfect. It's at the 5% capacity. It's normal. It's ideal. It's what we needed. Continuing. For number 7, A, to predict tonicity, we have the osmolarity of a solution before it's added to the body. For this analogy, that's like saying we need to know that only 5% of helium can go into the balloon before it becomes disfigured. That's our special number. That's perfection. And if it doesn't hit 5%, then we'll see it be smaller in comparison to other balloons that have reached that optimum capacity, or also known as osmotic equilibrium. And secondly, we would need to know that we're dealing with whether it be helium itself or a tennis ball. Now, once that's figured out and we know what's trying to go inside the balloon, we can determine whether these said particles can cross into the cell or not. Once knowing these two things, we can move forward. A hypotonic cell would be represented by an overinflated balloon, as I have shown in box 5. It's disfigured, being due to there being too much helium within it. A hypertonic solution is also shown there, which means that there isn't enough particles going into the cell or the balloon. So it's represented with a smaller circle or a smaller balloon. While an isotonic solution would be the ideal cell or balloon that's neither gaining nor losing particles, or helium in this case, and is at equilibrium. Lastly, so first things first, you should already know that the osmolarity of a normal cell is 0.3, and that 0.9% NaCl has an osmolarity of 0.3 as well. And one last osmolarity you should be aware of is that 5% dextrose also has a 0.3 osmolarity. I would recommend that you remember these for future assignments just because they really could come in handy. But if you don't, you can always just, use the formula and figure out the equation. Anyway, so as you look through my work, you will see that I did write down why 5% dextrose is so special. Dextrose actually needs glut in order to move into the cell. But as soon as it moves across the membrane, it actually starts metabolizing, like as soon as it crosses, which, to make things simpler, is in a way saying that it disappears, it disperses, it's no longer there as one, So now because it's metabolizing as fast as it does, that just means it's disappearing. So eventually that 5% dextrose will become a 0 as an osmolarity, or as its osmolarity, thus making the overall situation hypotonic, because after dextrose moves inside the cell, it disappears. So now the only osmolarity left is that of inside the cell, which makes the cell fatter than the outside. So it's as if saying 0.3 compared to 0. Now, moving on. When talking about 0.9% NaCl, it's actually an isotonic equation because, a cell's normal osmolarity within is 0.3. And 0.3 just so happens to be the osmolarity of 0.9% NaCl. So because they're equal to one another inside and out, they have reached equilibrium, which means that this whole situation is isotonic or equal to one another. Now, moving on to figuring out the tonicity of 3.3% dextrose added to 0.9% NaCl. As you can see on the paper, I did work everything out, so I'm going to explain the math portion of it before explaining everything else. So to start off, when taking 5% of dextrose, it can be split into 3. If you split it into 3 parts, each part would equal 1.67. And if you were to add 2 of those parts together, it equals 3.3, which is the amount of dextrose we need. So now that 3.3% of dextrose is known as 2/3, of 5% dextrose is what we need to find. So the last third of the 5% dextrose is the last third, which is the variable that we need to find. Now, because we know that we're only looking for that last third, what you did to one side, now you have to do to the other. So you divided the 3.3 by 3, the 5% by 3 to get 3.3. So you have to do the same thing to the 0.9% of NaCl. And when divided by 3, that 0.9% turns into 0.3%. So you would then have to also divide the osmolarity of the NaCl. So it would be 0.3 osmolarity divided by 3, which comes out to a 0.1 osmolarity total. Now, after you have all these variables, it's really just simple math. You just have to take the point of osmolarity of 3.3% dextrose, add it to the 0.1 osmolarity of 0.9 NaCl, and your outcome will come out to be 0.3 because you take 0.2, add it to 0.1. Now that we have a final osmolarity of 0.3, it's equal to a normal cell's osmolarity, thus making this solution isotonic as well. All right, so to conclude this video, I would just like to thank you for your time, and I hope I did well explaining everything. Have a nice day.